Hey guys, I wanted to go through and do a bit of work on incline ramps. So this is something the year 10s are doing a practical on, but I'm going to demonstrate some component vectors, which is what the year 11s are doing, and if the year 12s are watching this, well, it's just a bit of revision for you guys. Okay, so we go through a couple of things to start off with. I've got two ramps, ramp A and ramp B. Okay, as you can see, you've got two carts in purple. They have the same mass m. Now the distance of that and the distance here, they're the same. I did that intentionally, but the angle is larger. So this is a steeper ramp. So I'm going to demonstrate how you can use vector components to demonstrate the difference in the force and thus acceleration. So what I'm going to do, actually before I do that, let's go through some key terms, first of all. All right. So first term is mass. A mass is a measure of the object's resistance to change in motion. Okay, so that's independent on gravitational fields. So if you've got a mass of objects, independent on, regardless of gravity, as we can see from Newton's second law, the amount of acceleration you get out of that is related to the mass. In fact, is inversely proportional. If you double the mass, you'll get half the amount of acceleration for the same force. Okay, so that's important. All right, now, weight. Okay, let's bring that up over. All right, weight is the force that acts on the body due to its mass inside a gravitational field. All right. The other one I'll mention is Newton's third law. If body A provides a force onto body B, then body B provides a force onto body A, which is equal in magnitude and opposite in direction. Okay. So let's just focus back onto our planes here. All right, so we've got ramp A and ramp B. Okay, we're going to start off by drawing a vector that represents the weight. Now, weight equals mass times gravitational acceleration. Okay, that's a bit better. So these have the same mass, so thereby they have the same weight. Gravitational acceleration is constant at 9.8. All right. So I'm just going to draw a vector to represent the, pardon me, to represent the weight force. Okay, let's pick a different color. All right, so I'm going to make that a certain length here. So it's going to be 2 units going down. So that's my weight force. Now the weight force on this one is still the same. I'll draw that from the center of mass. 2 units down. That's the same weight force. And you say, well, if it's got the same weight force, how come the one, we know that the one that goes to the steeper ramp is going to accelerate more, it's going to be faster by the time it reaches the bottom. This is true, and we'll show why. Okay, so what we're going to do is we're going to use our geoliner, and we're going to find vectors that are parallel and perpendicular to the slope. All right. So I'm lining this up over my vector. I'm just going to put a little dot over here. All right. And I'm going to draw one that's parallel as well. I should do it this way. So I'll line this up so it's parallel and on the end here. And I'm going to, just to that one, I'm going to draw a nice soft line. Okay. And I might actually do the same over here. Just draw a nice soft line, joining up the dot I drew up the top with the end of this vector here. Okay. So what I'm doing here is I'm breaking this up into components. Now basically these two meet at a right angle. Okay, so this component here is a component going down the ramp. I'll just pick another color for that. Just draw it hot pink. Okay. So there's a, it's not a very good color. Not against the purple background or purple diagram. Let's pick another one. Actually, I'll just do it in pencil. Okay, so there's a vector component going in the direction of the ramp, and we've got another vector component that's going perpendicular to that. So we're going to add these two components to get up back to our weight force. All right. So year 11s and year 12s should know what this is about. Year 10s, don't worry too much, but just follow the explanation of what this means. Okay, so we've got the two components there. Now let's just do the same quickly with the other one. Okay. So while we're here, let's get this. All right. So just draw some guiding lines, parallel and perpendicular. Just nice soft lines. Okay. And then from there, just draw the lines where they meet. Okay. Okay, so what you notice here, let's just zoom that in. Let's do cuts. Okay, so that's my vectors. So you notice that this vector here, the one on top, running down, is smaller than the one running down here. The weight vectors were the same, but the components of those weight vectors, which are parallel to the ramp, are different. Okay, now you can actually work out what they are. So I'm going to put a little angle here. There's actually the same angle as that. I'm not going to use geometry to prove it, just trust me on this. Okay, and then that angle is different as well. So basically the component, force component down, oops, ramp. Okay, if you use trigonometry, so we're talking about this component here, and likewise that one there with a different angle. So, but I'll just write out for this one. Okay, so that force component is force, just call it force down ramp, equals mg, that's the hypotenuse, times by sine theta. That comes from your rearranging of trigonometry, particularly SOHCAHTOA. So sine equals opposite, so that's the opposite length up the top, over the blue hypotenuse. Sine theta equals opposite over hypotenuse. Okay, so but now we've got a formula for the force down the ramp. Now, the interesting thing comes with the acceleration. The acceleration down the ramp, from Newton's second law, acceleration is force divided by mass. Okay, I'm going to zoom that out a little bit. Okay, there we go. All right. So the actual acceleration of the body down the ramp, mg sine theta divided by m, and the two m's would cancel. What this means is the acceleration isn't actually connected to the mass. Okay, and that actually is an important consequence of this. So the acceleration is basically part of gravitational acceleration g. If this was like 90 degrees, the cart would just fall straight downwards, and you have, well, that sine 90 is 1, times by g is just gravitational acceleration. All right, so basically the larger the angle here, up to 90 degrees, the larger the acceleration. That's what's going on. Okay, so in the case of the second one, well, we saw it with the vector, but increase that angle from theta to phi, because phi is bigger than theta in my example, then you get increased acceleration. Okay, the other part I'll just make mention is I mentioned Newton's third law. This component that goes into the incline ramp, well, that's going to be opposed by Newton's third law. So if you're pushing down onto the ramp, normal to the ramp, you get that normal restoring force back up. So that's taken care of, unless it breaks, and then that tells you that, or deforms, that tells you that it wasn't able to maintain that force. But our ramps are going to be nice and strong. Okay, so let's just go through some of the consequences of what we just discovered. All right. So year 11s, you're going to start doing Newton's equations of motion soon. So year 10s, this would be unfamiliar, and year 12s, this would be revision. Okay, but we've got three equations of motion for uniformed accelerated objects. In particular, I'm going to pay attention to the third one. Okay, so remember our A was dependent on the angle and the constant gravitational acceleration of 9.8. All right, so right now, this is the kind of the things that the year 10s, you could change the mass, you could change the distance it travels down the ramp, or you can change the angles. Now I'm going to go through and explain what is going to happen in terms of what happens when you get down to the bottom of the ramp. All right. Okay, so let's have a look at the three scenarios. Okay, I'll zoom that out so you can kind of see both the ramp and the explanation. Okay. There we go. All right, so if you increase the distance that you travel up the ramp, or down the ramp, I should say, so you start from a higher point up the ramp, so this distance here, you get the same acceleration. So you haven't changed anything about the acceleration. The only thing that actually changes the amount of acceleration you get is theta, unless you want to jump on another planet that has higher surface gravitation. Okay. So you get the same acceleration, but you've got further to travel. So if you travel further with the same acceleration, you pick up more final speed. Now, the initial speed is 0 for this. So basically, v squared, final speed squared, equals 2 times acceleration times by distance. Okay, and if you increase your distance, you increase your final velocity. So if you start up higher, you accelerate at the same rate, but you've got further to travel, so you'll pick up more speed. Okay, the second scenario is you increase the angle, and as we saw before, that increases the acceleration. So A increases, but we're assuming that you've done this right and you had a fixed position on the ramp that you use every time when you change the angle. So as you increase the angle, you increase the acceleration, same distance that you travel down the ramp, so you end up with a higher velocity because of an increase in acceleration. Okay. Now, the interesting thing is, if you increase mass, now, as we showed before, acceleration, it actually cancels out, because the force had mass in the equation, and when you divided out the mass to work out acceleration, you end up cancelling both masses. So acceleration is independent on mass. And what happens is, for increase in mass, final velocity is constant. You might think, hey, that doesn't make sense. In the extended practical, that comes down and collides and it pushes it further. Well, it's not because it picked up more speed, it's just because it's more massive. So mass, remember, is related to inertia. So if you have a more massive object, even if it's traveling at the same speed, it's going to be harder to stop. That's really what it comes down to. And for the other cases, you kept the mass constant, and in both scenarios, you actually increased the final speed that it reaches at the bottom of the ramp. So in these two cases, it will so if you increase s or theta, you result in having more speed at the bottom. If you increase mass, you don't, but you have more mass. Either way, in all three scenarios, it's going to mean that your little fence over here somewhere, so you go down, you collide with your fence, and you measure the distance across there. So whatever that distance is, is going to be larger if you increase any of these, but for different reasons. Okay, so I hope that gave you guys some insight into the Year 10 practical, breaking down components, and I suppose just a revision for you guys in Year 12. All right, I'll catch you guys later.